Hello there. In this video, we are going to be covering time-dependent batch arrival distributions. And actually, in a very similar way as we've seen with customizing probability distributions, you can also simulate state-dependent or individual-dependent batch arrival distributions, but we'll just do time for now. So let's begin, as we usually do, with importing the Ciw Python package. We need that to work with Ciw, obviously. And we're going to define a time dependent batches distribution, and to save ourselves from implementing other stuff, we'll just inherit from Ciw this distribution class, and then we need to define our sample method. So this is an instance method, so we need to pass in self, and we'll pass in t is time, and ind is for individual. Great. Now let's say that when we're thinking about the batch arrival distribution, that we want to be changing based on time the size of the batches. So just as a simple rule, let's say if the time is strictly less than 10 or 10.0 or whatever, then the batch size is 2. So they arrive at in batch sizes of 2 if time is less than 10, and otherwise, let's say it returns 1. So we've got this change in the behavior of the statistical process. Okay. Type system is getting a little cranky with me, so I'm just going to, let's see, I guess I'll say this could be none or a float. Should probably make it happy. Yes? No? Sometimes it does take a little bit of time for it to kick in too, though. Okay, no, I guess that's correct. It's basically saying if this is none, then it's not well behaved, which is true. I haven't handled the none case. But you know what? We're not going to fix that right now. It's not a hard thing to fix, but it's not important to fix it right now. The basic idea is that you're going to pass in a float. And if that float is less than 10, this isn't the only fix you could do, but I will do a simple fix just because the code is annoying. The warnings are annoying. Let's say that by default it's 0, but that's fine. Okay, so t is strictly less than 10, so if the time is less than 10, the batch arrival size is 2, and otherwise it's 1. Okay, great. So let's actually set up a simulation by defining a network. So q dot, and we'll do create network. And then we've got our arrival distributions. We'll pick some arrival distributions here, deterministic. So I'm just following the documentation example, actually. So we'll say deterministic of 3 for the arrivals. And for the service, we will set it to be 0.5. Oops, a little bit of Vim magic there going crazy on me. And we'll set our batching distribution to be our custom time dependent batches distribution class instance there. And then the last thing we always need to specify here is something about how many servers are going to be available. In this case, we'll say 1. And right, we need to say that this is service, not arrival. Now we can run the simulation, so we'll go sim is equal to q, not equal to, but you know what I mean, assigned. And we'll pass in our network, and then we will simulate until some maximum amount of time. And for this example, we'll run for 16 units of time. And then just for the sake of example, we'll grab sim.nodes, and we'll grab the last node, the exiting node, and just grab all individuals. All individuals. We are all individuals. Okay. And we have 8. So that should roughly make sense. Let's see. We've got the arrivals are occurring every 3, and for an amount of time of 16 units of time, there should be 15 arrivals. And so of those 15, how many should have completed their service? I don't want to really do the math in my head, honestly, but we've got every 0.5, which is substantially faster as a rate than this. So they should be happening pretty quickly. And then there's also the 2. I don't think I want to do the math, but basically I'm not overly surprised that 8 comes out of simulating for 16 units of time. Kind of makes sense. They explain the math into docs, but in the docs, let's see what they say. So we'll simulate for 16 units of time. Now at times 3 and 9, we would expect 2 customers arriving. That makes sense. A total of 6. And at time 12 and 15, we would expect 1 customer arriving, a total of 2. So 8 customers in total should finish service. Yes, okay. And that's provided the last little detail that this is fast enough, which I'll trust that it is. Okay, so anyway, the real substantive point here is to say, just like other distributions we've seen, you can subclass to make your own batch arrival distributions. And in fact, you don't even have to declare in the distribution name that it's a batch distribution in the name of the class. That's fine, whichever way. It's just from a Ciw simulation point of view, I should say the Ciw Python package point of view, that it just needs to be a subclass of distribution and it needs to return integers. Those are the key things. And to have time dependence, it just needs to be a function of this parameter time. So with that, I hope you find that useful in maybe setting up time-dependent batches. Maybe, for example, you're simulating a service where a bunch of people wait outside of the door, and in the first few minutes, there's a few clusters of people who come rushing into the service, and then after that, maybe it's a bit calmer, that this is the type of thing that you might use a batch distribution for. With that, I will catch you in the next video. Have a good one.